Welcome to Smart Asphalt, the podcast where we dive into the latest innovations transforming the asphalt industry. We'll be talking to leading researchers who are rethinking how asphalt materials are specified, how they're designed, how they're tested, how they're constructed, and how they are maintained. So whether it's developing more resilient pavements, enhancing sustainability, or optimizing performance, in each episode, we're just going to shed a little bit of light on some groundbreaking work that's being done in the paving industry so that we can be paving in a smarter, more sustainable way. My guests today are Dr. Shen, Dr. Yu, both from Penn State University, and Mr. Richard Steger with Ingevity. And we're going to be talking about the use of a wireless particle-sized sensor for assessing workability. But before we get there, I would like our guests to introduce themselves and then we'll get started. But maybe I should introduce myself as well first. I'm Dr. Amma Agbedor. I'm with the Asphalt Institute. And let's start with Dr. Shen to introduce herself.
Hi, thank you, Emma. Hi, everyone. My name is Shihui Shen. I'm currently working at Penn State University as a professor. So I work for Penn State Altoona campus, and we have a rail transportation engineering program here. I have been working for asphalt industry for almost 15 years. So nice to talk to. I'm very glad to have this opportunity to share some of our recent research on workability and asphalt mixture compactability. So very nice to talk to everyone today. Thank you.
Thank you. Dr. Yu, please introduce yourself.
Hello, everyone. My name is Shuai Yu. I'm an assistant professor in Penn State Altoona, and I received my PhD in Penn State as well. And right now, my research is primarily on the civil engineering material and also the application of the artificial intelligence into the construction and the health monitoring of the infrastructure. And thank you, Amma, for this opportunity to share our research findings. Thank you.
Awesome, thank you. And Mr. Richard Steger.
Hi, Emma. My name is Richard Steger. I'm with Ingevity. I'm in the research development, technical support / advocacy role. I've been with Ingevity for about 13 years and about, 35, 37 years in the industry.
Great. Thank you all so much for joining us. And as I mentioned, this episode is going to be looking at workability. And if you're in the industry, you probably hear about the term workability a lot, but there isn't really a clear way of measuring it. We have different methodologies for having an idea of how workable a mix is, but I'm gonna let Dr. Shen give us more information about what workability is and how it's being measured so that we can get into some of the research that they're doing to improve the way that we measure workability.
Okay, so thank you, Emma. So I'm going to talk a little bit about our understanding about the workability. So workability for asphalt mixtures is a very important property. As we all know, if a good workability can help distribute particles move more effectively during the compaction so that it can reduce the voids and improve the structural stability of the mixtures. And improve the workability can minimize the cracking, deformation, and ensure the smoothness of the pavement, and also ensuring the durability under a long-term traffic loading. So that's very critical. And the workability and compactability, it's a test. We can ensure we might have a long-term good performance of the asphalt pavement.
Great, thank you so much. And so understanding what workability is, I guess, could you tell us about how this led to your research into this SmartRock technology?
Yeah. So the history of the SmartRock can be dated back to year 2014 and 15. when Dr. Hai Huang from Penn State Altoona, who is an expert in rail track research, is looking for a tool to monitor railroad ballast performance and behavior. So under the funding from Federal Railroad Administration, Dr. Huang invented a wireless MEMS sensor, SmartRock, to mimic the behavior of railroad ballast under train loading. The first generation SmartRock is about 33 millimeter, so the external shell can be 3D printed, or so that it has the exact shape and angularity as a ballast particle. Inside of it, it includes a number of sensing units, so it can measure the translation, rotation, acceleration, temperature, and contact force of the particle. The service temperature of the first generation SmartRock is about up to 80 Celsius degrees, and it has a sleep mode function to save battery life. Since its development, the railroad version, or say the large version SmartRock, has been widely implemented in railroad research to study the ballast stability, the geogrid performance, and the track conditions. So then, as a pavement researcher, I see SmartRock can be a great tool for researching asphalt mixture behaviors, because asphalt mixture is also a type of particulated material. So I collaborated with Dr. Huang to make modifications to the railroad version SmartRock. Then two major modifications were done here. The first thing, we redesigned the internal sensing unit to an overall size so that it can be reduced to 27 millimeter. And we also made the sensor more high temperature and high pressure resistant, so it can accommodate at least asphalt mixture compaction temperature. All other features like wireless data transmission, rotation, acceleration measurement, and sleep mode capabilities all maintain the same. The newer version SmartRock is trademarked as SmartRock and was implemented to study many asphalt mixture behaviors, including the workability characteristics we are discussing today.
So I guess based on that background history, you engaged in this project to figure out workability parameters that you could use, because you have to have a way of measuring it, right? And I guess that's the work that was done by Dr. Yu, so maybe you can give us some information about that.
Okay, so I'm gonna use several minutes to introduce how we used the SmartRock to do our workability analysis. So during this asphalt mixture compaction, we have a central hypothesis that is the motion characteristics of the asphalt mixture particles have a direct impact on its workability and compactability. But before our research, how this particle was rotating and moving under the compaction load is still unclear. So with this aid of the SmartRock, we can just successfully monitor the particle behavior during the compaction process. So as this picture shows, we just put our SmartRock in the center of the asphalt mixture during the compaction, so the sensor can collect this particle rotation and motion throughout the whole compaction process. And here just shows the Euler angle of the SmartRock in three different directions. And we could notice that this SmartRock just follow the cyclic rotate throughout the compaction and in all three directions. And we all notice that the amplitude of this Euler angle is also different at the beginning, at the middle, and at the end of the compaction. So here, we just declare a new parameter, that is relative rotation, which is the differences between the peak and valley of the Euler angle of the SmartRock for each gyration. And during the compaction, and we just collected all of this relative rotation curve, and it shows here. So we could notice that at the beginning of this compaction, the particle rotation is more dramatically. And when this, asphalt mixture particle contact to each other, and also the material densified, this relative rotation starts rapidly decreased and also stabilized. So that is the relative rotation curve during the compaction. And we notice that this relative rotation curve is very similar to the change of the mixture height. So using this same figure, we put these two curves together. Just the orange curve is relative rotation, and this blue curve is the height of the asphalt mixture. And we surprisingly found that these two curves is very close and even overlap to each other. And then we calculate the Pearson correlation coefficient and get a very high value. And that indicates a very high correlation between this relative rotation and this mixture height. And also because during the compaction, the asphalt mixture, the weight is unchanged. So the height is also a very good indicator of this density. So we could see that the relative rotation and the density of this asphalt mixture is highly correlated. So, and that correlation is the foundation of our using our smartly to characterize the workability and the compactability of this asphalt mixture. Here, I just want to continue to introduce how we can also use the rotation parameter to evaluate the workability of the asphalt mixture. So we have this curve of this relative rotation, and we thought if we could define a parameter that more clear to quantify this workability of the asphalt mixture. So then using this curve of the relative rotation, and we defined a relative rotation capacity, that is the area under this curve from the initial number of gyration to the design number of the gyration. And the higher of this relative rotation capacity, or the RRC, that means this asphalt mixture particle moves more dramatically, and that means the workability is better. And here's another parameter. So if we want to compare like this workability between two asphalt mixtures, one way is we can use like two relative rotation curve and use these two curves to do the comparison. But we can also use another way that get the differences between these two relative rotation curve, and we call it a residual rotation. Okay, so this is the residual rotation between these two mixtures, and if we call it residual rotation. So if the curve of the residual rotation is positive, so that means the first mixture has a more active rotation or better workability. So if this curve is negative, that means the second mixture has a better workability. And we also defined a new parameter, average residual rotation, ARR. That is the average value of this residual rotation from the initial number of gyration to the design number of gyration. So here we can use the curve of this relative rotation or the residual rotation to evaluate the workability of this asphalt mixture. And we can also use rotation parameter, this relative rotation capacity, RRC, and the average residual rotation, ARR, to directly quantify this workability of the asphalt mixture. And this two curve and this methods was also standardized by the ASTM committee, and you can just find this standard text methods online. And I also want to give you a very small example and to show how we can use this curve of this relative rotation and the residual rotation to evaluate the workability of the asphalt mixture. And here just shows two mixtures, the mixture 1 and mixture 4. They are compacted at the same temperature, but the differences of the additive. So the mixture 1 with use 0 additive, mixture 4 with 0.7% of additive. The additive is alcohol, by the way. And so we just plot this relative rotation curve of these two mixtures, and we could see that the blue curve, that is the with additive, and this purple curve, that is without additives. So from this curve, we can notice that the asphalt mixture with additive shows the particle rotate more dramatically, and thus the workability is better. And also, we can use the residual curve, that is residual between this mixture 4 and mixture 1. So we can notice that this curve is positive. So that means the first mixture, which is with additives, has the better workability. Okay, so that is, we can use the curve of this rotation to just evaluate the workability of asphalt mixture. And we can also use this method to just like evaluate the mixture like HMA, WMA, and recycled material, include like RAP and plastic polymers. And we did all of this research, and this curve and these parameters all works very well. Welcome.
Great, thank you so much for that explanation. And I really like the progression where you were able to link the measurement of the workability to parameters that we can recognize in our super pave design methodology, like an initial. And so I'm starting to see, and then you went into how you were calculating the workability, comparing different additives, and you mentioned how that can be used for different modifiers. I think that's really interesting because I see the direct industry application as you start to talk about it. And so I guess this is a good place to bring in Richard to talk about how you got introduced to this work and the industry application that you see.
Thanks, Emma. Again, the way I was introduced to this technology was initially through a poster presentation at TRB. So I talked with one of Dr. Shen's graduate students at the time, and she indicated that they were working on this, and so I kept track of it for a couple of years, and eventually they had another poster, and so after that, I believe it was Schwei's poster on that one, and so I followed up with him, got in touch with him, and as you've already seen him explain, it determines the difference between additives, a mix with an additive and a mix without an additive. And coming from an additive supplier, my position with Ingevity, that was of keen interest because we have long struggled to try to identify a way to measure workability in the mix and quantify that in the laboratory. There's a lot of other methodologies that are out there, and some of them work better than others. But I found that this one worked pretty well, and so I thought that if we're going to do something with this, maybe I should investigate it more. So I initiated some internal research with Dr. Shen and her research group. We sent them materials. And in fact, that was some of the data that you were looking at there just previously. So that work showed to me that this method works. It can tell the difference between a mixture that has an additive, doesn't have an additive. It can tell the difference between a mix that's at a higher temp versus a lower temp, or the combinations of those things. It's sensitive to the dose rate. It's sensitive to the temperature. And if you can imagine from a supplier standpoint, developing additives, that it's good to be able to test that in a laboratory setting, and it's good to see that this device could pick up. It's sensitive enough to pick up the dose rate. That was another thing that was very unique about this particular approach. So that's when we initiated the process. I approached Dr. Shen and asked her if she was interested in trying to standardize this through ASTM. I've been active in ASTM for 20 plus years, and so we pushed this through one of the committees at ASTM, and we were successful in establishing a test standard for that. So as you can see, some of the text that's on the screen, you can see, how can this be used? You can obviously use it to evaluate a warm mix additive, whether it's evotherm or whether it's any sort of surfactant type additive, chemical additive in the mix. You can use this particular approach. You can relate your lab workability to field workability. You can evaluate your mix workability in the laboratory at various temperatures, so you can see which temperature is the best temperature to use during the production of the mix. What challenges does this address? This, as I mentioned, creating a repeatable method was very desirable, and having it standardized makes it much more useful to the industry, because different agencies can specify this particular approach, and they can reference this standard test method. And then again, I think it also takes a lot of the guesswork out of understanding how workability occurs within a mixture. Shuai did a great job of explaining how that works, and so that's what impressed me, and that's why I thought this was a good way to go and a good approach. And I think that owners can use this. If you're a mix designer, you can use this approach to help you select the best warm mix additive for your mix, and it also can help you determine what's the best production temperature.
That's great. Thank you so much for making that link. And we always love to hear about research projects that are practical and make their way from academia and become implementable in the field. Those are the best. And so I'm wondering, what is kind of the future? We have an ASTM. We have some real bullet items here of how that standard can be used, whether by mix designers or owners. So I'm wondering if maybe Dr. Shen, you have some ideas of the future for this project and the Smart CLE technology.
Absolutely. Yeah. Regarding the future work and the implementation, with the availability of Smart CLE sensor and ASTM specification, as Shuai and Richard mentioned, I believe this technology can be applied to a wide variety of asphalt mixtures, especially for modified mixtures, like we have been using wraps and plastic modified mixtures, and also like rubber modified or warm mix technologies, and to see how these mixtures might perform in the field under the compaction conditions. And so this will be a good quality control tool, so that the results can be used for mix design stage to screen out some potential poor mixes, such as tender mix or the mixes that are hard to compact. And in the meantime, currently we are establishing a database to capture the relative rotation and workability of a wide variety of asphalt mixtures. By using the machine learning algorithms, we have developed a quite successful density prediction model, which allows us to use laboratory geometry compaction data based on ASTM D8541 standard to develop a field compaction curve, as you see here. The curve presents the density level at a certain number of roller passes, which can help the paving contractors to estimate roller passes, adjust the roller control parameters such as frequency, amplitude, before and during compaction cycles. If you are interested, this work will be presented at the 2025 TRB presentation, so feel free to check it out.
Okay, great. Thank you for sharing that. Now, I understand that this is a new technology. So what's the availability of this technology if agencies are interested in maybe starting to either specify it or even just kind of research their materials with it?
Yes, to help the industry or agencies implement this technology more conveniently, we have developed a full package of graphical user interface and data analysis software in collaboration with RTS, which stands for Railroad Technologies and Services, and Instrotech companies. If you have any questions about how to obtain the Smart CLE sensor and the data analysis software, please feel free to contact myself or Mr. Maurice Abeles, the Vice President of Marketing and Sales from Instrotech. So I'm sure any of us can help you for getting the sensors. Okay. So finally, I would like to acknowledge the collaborating partners from industry and agencies as listed here. So we look forward to more collaboration opportunities in the future.
I'm very excited for the work that you've done, and I'm fairly certain that, especially with the field project that you have going on and the database of collecting how the sensor is monitoring compaction in the field and what it's going to translate to performance, I'm particularly excited about that because I see potential for it being tied to intelligent compaction and moving forward with having mixes that are optimized for density, because it's very well known in the industry that compaction and densification of the mix is the #1 factor that influences performance. So it looks as if you are working on projects that are going to help us in ensuring that we're achieving our goal of having good performing roadways. So thank you all for sharing your thoughts with us today. And thank you for your attention, for those of you who are listening, and we appreciate your time, and we'll see you on the next episode of Smart Asphalt.